The second part about lifespan, I published it in 2 papers before this book, The Physics of Life. Published them under the headline, Why the Bigger Live Longer. And the question is inspired by a very well-known trend in zoology. Actually, it's called animal design. Bigger animals live longer. You see this in the same species. Dogs, tiny dogs have short lives compared with big dogs. Why? But of course, I'm not a zoologist. Remember the joke? I cannot be accused of being a bad biologist because I'm not a biologist. Yeah. But I know a lot about zoology. My father was a veterinarian, and he was very good at not keeping secrets about what he knew. It's obvious. Animals are the way I describe them, but that is to describe, not to predict. So the question here is about predicting. And the flavor of this course is that if it's good about animals, it should be good about anything that moves, such as. So I start the list here. Animals, yes, that's boring. And then vehicles. I mentioned the B-52. Compare the life of that architecture. It's a flying house or a flying fortress, whatever you want to call it, compared with something much smaller that moves, say a moped. Rivers, they move. But the tiny ones, like the milk spilled on the kitchen floor, obviously doesn't travel far, which means it doesn't live long. See, travel and life are the same thing. I already erased that. So live is to travel. Rivers, the winds, the jet stream. It runs everywhere from wherever it came. Nobody knows, but it goes around the hemisphere, northern, and then another one around like a halo, the southern hemisphere. So winds, the bigger, bring air farther. And then, of course, solid stuff, rolling stones. You've seen movies of rock slides. They fall on a highway, and an automobile, no matter how fast, cannot get out of the way because the rock is rolling fast and long because it is big. See that? And rolling stones are solid. Rolling blobs of fluid, rolling inside fluid, are called turbulent eddies. All of them exhibit this animal feature. Now guess, to predict why the headline should happen. I told you the wise joker in science is to start the easiest way. So I started to write about these things from this bottom end. So today I'll show you how to predict the idea, to predict the phenomenon by thinking of rolling stones. It goes as follows. Now, think that just keep it to yourselves. Don't share this with the authorities that animals are rolling stones. Those guys have died already, almost, the Rolling Stones. Some of them are still surviving. And yes, yeah, I like them. Ask me why. Mick Jagger, is an Arsenal fan. Oh yeah, this counts. This really counts. Okay, so here's one Rolling Stone. It's rolling to the right with a speed v, and obviously it has the mass m, therefore the weight mg, and its movement is slowed down by a friction force F. And F, this is elementary stuff. F is proportional to the weight, and mu is a friction coefficient, and then mg. In the beginning, which is what I sketched here, this boulder is moving with this speed. It means it has an inventory of kinetic energy that's equal to 1/2, and then the density of the rock times v squared. No, that's not what it is. 1/2 mv squared. Okay, and the rock rolls until it slows down here to v equals 0 at distance L. And to get there lasted a lifetime called T for time. You see here, lifetime means life travel. The question is how to predict these things. And to predict them by accounting for the fact, according to thermodynamics, that the energy in this moving body, which is the kinetic energy, is dissipated through friction and then heat rejection to the ambient, dissipated completely until that end, meaning that the kinetic energy, which I'm going to write as mv squared, as an order of magnitude sense, is the same as this friction force times L. Never mind the fact that the friction force decreases in time because the speed decreases in time, but the order of magnitude of dissipation must be the same. In fact, it should be a one-to-one relationship between dissipation and then the original kinetic energy inventory. See that? So this is the only equation of importance. In fact, I rewrite it as mv squared, and then here F is mu mgl. And from that equation, you get the life travel. So these are results. Life travel is v squared over friction coefficient times g. And then from the easy to remember fact that L divided by T is the order of V, meaning you can eliminate one of these V's and get the scale of the time or lifespan, which is V over mu Fg. So these are the two results. They don't say much except that they answer your gut feeling that more initial momentum is good for a longer travel and also for a longer life. But these are predictions that cannot be refuted. I'm talking about in a scaling sense. Another observation that will that appears here for the first time is that t varies with speed the same way as square root of L. So lifespan varies as square root of life travel. Let's see what that means. If you, I don't know which one to put on the abscissa. If this is the travel, this is the lifespan, then that's the behavior. Moving farther, when you're old, does not make you live longer. Did I read my drawing correctly? I've never made this sketch this way. You can tell this kind of aha your own way. All right, so this is the kind of the hard facts, but we're not bored yet. Okay, we happen to be in a drinking bar of ideas. What else is hiding behind them? I do remember the moment when I said this answer to this life and death question cannot be so simple. There must be something else. And here it comes. How many rolls does this rock execute until it stops rolling? So that number of rolls is the lifetime divided by the time it takes to roll once. But wait a second, this rock is not rolling. This rock just came off the hill. It's not spherical. This is not a ball bearing that's rolling on the highway. It is hurtling. And its trajectory is this way. Meaning the rock is definitely rolling, but when its high spot is hitting the ground, the rock jumps. And it jumps, there's nowhere to jump except to a height comparable with its length scale. So this height is the length scale of the body, meaning that the mass of the rock is rho d cubed. We've done this for the fish, for the bird, for everything that is moving in this course. And it is from this thing earlier, if you remember the theory of locomotion, for example, that of the human wheel, or it all boils down to the speed of free fall, in this case falling forward. That speed of free fall is the famous formula of Galileo Galilei. So the Galilean speed of falling forward is the square root of g, and then the length scale from which the fall originated. And that means that this speed, which I just wrote, also varies with m as m to 1/6. This is the trend that unites all animal locomotion, if you remember those formulas. So if you take well, so I've got two formulas. One is for D, and the other one is for the time scale of one roll. The time scale of one roll, which I will write immediately. In other words, it goes as follows. If the speed is v, then v times the time of one roll is d. And from this you get the time of one roll, which is d over v. And then you can substitute this idea in the definition of the number of rolls, and also use this. Where is it? This is the time scale of the life of the movement to the right. And so if this is 1 and this is 2, then this is 1 and this is 2. And when you make these substitutions, you get, meaning if you don't believe me, you should make these substitutions yourselves. You get a result so simple that it tells you that you are right. You, the person with the question, the person with the attitude. So the answer is that n is of the order of 1 over the friction factor. Okay, let's read this. If the friction factor is high, and when it comes to rolling, high friction, meaning something that rolls that's not perfectly round, that thing has a friction factor. I've not looked in the handbooks for a while. Say 0.5 in that range. A ball bearing, on the other hand, has a mu that's smaller than 0.1. So high friction factor, few rolls. Low friction factor, many rolls. Not bad, huh? In fact, we'll come back to this little conclusion in a second. There's another thing that I forgot to write down because I got too excited. If you, if in these results for the life travel and the lifespan, you replace V with what I wrote earlier, where was it? Here, and some other things. Alternate expressions for life travel and lifespan are the following. For L, you get in terms of body mass divided by rho to power 1/3 divided by the friction factor, and for the life time you get m divided by rho to power 1/6, and then mu f and g to 1/2. This is a rewriting of those two expressions. And one more time, they reveal that the lifetime varies as the square root of life travel. All these, formulas, there are so few, they all kind of come from the same mother, which is over here. All right, so number of rolls goes inversely with the friction factor. But also going inversely with the friction factor is the life and the travel. But you have the Constructal law, this statement that the universal tendency is for movers to evolve, which means to change their configuration, to achieve greater access, which means to keep moving, not only in time but also in space. If you invoke that law, you predict that in time, this friction factor should decrease to have greater L and greater T. At the same time, of course, the number of rolls should increase. But all of that happens because this rolling rock has freedom to morph. It becomes rounder, not the other way. If it becomes the other way, say it splits into, two halves, it's always two halves and 3/3 and so on. Then that is the end of that kind of roll. That is a big mu f when the rock splits. But the rock that stays intact has no future except to become more and more spherical. In fact, the manufacturing of ball bearings is exactly that. Do you know how they make them? They put a kind of a slug of steel between two big abrasive stones, and the stones are doing this. The way that my grandmother was making dumplings. And you do this enough times, and that thing becomes spherical. You've never seen this? For example, in this country, you can still buy spherical donuts. They are not made this way. They have some template to cut them to look so cute. But in the old country, meaning all over Europe, they would make these. They're called. Who knows German here? Because all of that comes from Germany. The pretzel making, it's a German thing because it was cold there. Yeah. So this is how you make a sphere mechanically. How else? You're not going to stick it on a spindle and put it in a lathe. No, absolutely not. Okay. So the evolution of the direction of things in nature, in this case through erosion, is constructal. You know that this mu f is destined to decrease if the rock is moving. This little example, having arrived at why rocks becomes more and more round, is an introduction to a whole list of exclamation points. Is that human movement has evolved in the same direction of easier rolling. I hope I impressed you with the drawing of the human biped as a rolling wheel, a wheel with only two spokes. Well, that was the original design. And then, people don't know when, but about 10,000 years ago, the wheel appeared, the human-made wheel. And the wheel evolved from solid to one with few spokes, as in the emblem for the Volvo automobile. Not a Volvo, Mercedes. I told you that story. Yeah. Same direction of configuration change as for the rolling rock. Is that way with a river? The erosion in the river basin, in the river channel, You can call it friction, you call it bad news, I don't know what you call it, but the water has a mind of its own. All right. Oh, when we reconvene, we'll tell the same story by Howard joke about the fact that if the stones and the air are the same medium, say water and water, then you have turbulent eddies. So the turning eddy is that body, the one that I sketched here, and the substrate all around is the same material, meaning water, and the eddy does the same thing that I drew here for the rock. The eddy moves while retaining its identity, moves to a predictable distance, predictable according to me, during a duration that's predictable. Why? Because the eddy is the same as the rock, but the rock has melted and now it's moving as an eddy in a pool of the same lava, you see.